Hi guys, so today we're going to transition from looking at just the cubic function to looking at just polynomials in general and looking at how to graph those. So in order to graph polynomials, we need to know what a polynomial is. So over here that lists some characteristics of a polynomial. So it says all the exponents are whole numbers. So an example of something that is not a polynomial would be like 3 to the x or x to the 3/4. It says no variables in the denominator, so 1 over x minus 2 is not a polynomial. No variables under a radical. And then the graphs are continuous with no sharp turns or holes. So the absolute value of x is not a polynomial. That graph does not have that polynomial characteristic. All right, so what we're going to do to start is just look at some vocab about polynomials. So the first one, it says that the degree is the highest exponent when a polynomial is written in standard form. So standard form just means that basically it goes in order with your biggest exponent ending with your smallest exponent. So this first one is in standard form. The degree in that form is just the highest exponent. So for a, your degree is 5. What we also know about the degree is it tells us the highest number of turns that this graph could possibly have. So some of these polynomials are going to do things like this. They're going to have those relative mins and maxes. Well, if your degree is 5, the most of those turns that you could possibly have is 1 less than that. So this can't have more than 4 turns in it. All right, looking at b, the degree of b would be 4, because even though it's not in order, it is the highest exponent. All right, then c is a little bit different, because c is an intercept form or factored form. So we need to think, if this were multiplied out, what would be my biggest exponent? Well, if I do x squared times x to the first times x to the first, that would give me x to the 4th. So this would still be a degree 4 polynomial. Something else that we need to look at with these coefficients, that we need to look at with these polynomials is the leading coefficient. So the leading coefficient is just the coefficient in front of that highest degree term. So on this first one, the leading coefficient is 3. On the second one, the leading coefficient is 2. And then on the last one, if this were multiplied out, well, there's 1, 1, 1, and there's nothing out here. So 1 times everything would give us a leading coefficient of just 1. Now, the reason that we need to know degree and leading coefficient is because it helps us to determine end behavior. So end behavior, up until this point, we've only had to determine end behavior from looking at a graph. Well, now we're going to determine end behavior from a polynomial function. So in order to determine that, we look at 2 things. We look at the leading coefficient, and we determine if it's positive or negative. And then we also look at the degree, and we see if it's an odd degree or if it's an even degree. Now, odd degree and even degree is not the same thing as the function being odd or even. So if you remember, we did that at the very beginning of the year. Odd or even functions were a little bit different, because that was, an odd function was where f of x is equal to f of negative x is negative f of x. Even functions were f of negative x is equal to f of x. Okay, so on this little chart, this is not a chart that you need to memorize. You just need to think about the things that we're putting in here. If it's a positive leading coefficient and an odd degree, think about the simplest polynomial that you know with an odd degree and a positive leading coefficient. Probably y equals x. Then think about what the ends of y equals x look like. Up to the right, down to the left. So then to fill in that end behavior, as x approaches infinity, y approaches infinity, negative infinity, and negative infinity. All right, still an odd degree, but a negative leading coefficient, we would think about negative x, which would look something like this. As x approaches infinity, y approaches infinity. Negative infinity. As x approaches negative infinity, f of x approaches positive infinity. If it's an even degree, easy function to think about would be x squared. On x squared, both ends go up, so both approach infinity. Negative x squared would be an example of an even degree and a negative leading coefficient, and negative x squared has both functions going down. So if it's an odd degree, they're in opposite directions. If it's an even degree, they go in the same direction. If it's a positive leading coefficient, we end up. If it's a negative leading coefficient, we end down. So on to, we're going to determine the end behavior. So in order to find end behavior, I'm going to write the statement and I'm going to draw what the ends look like. The reason I'm going to draw the ends is because when we get to graphing, that is going to be a step. So this graph has a leading coefficient that is negative. It has a degree that is odd. It's 5 because that's the highest exponent there. Negative leading coefficient and odd degree would look like y equals negative x. So to write my statements, as x approaches negative infinity, y approaches positive. As x approaches positive infinity, y approaches negative infinity. All right, looking at B. This one, again, we need to determine our leading coefficient. Well, that's all positive, positive, and positive. So positive leading coefficient. And then my degree. If this were multiplied out, that would be x to the 4th. So it is an even degree polynomial. Positive leading coefficient and even degree will have both ends going up. So as x approaches negative infinity, y approaches infinity. As x approaches positive infinity, y approaches positive infinity. All right, so this is just some extra practice that we did in class on Pear Deck. All right, so once we know end behavior, that gives us a really good start to our graph, but then we need to figure out what our graph does in the middle. So to figure out what our graph does in the middle, we're going to look at something called the multiplicity of these factors. So the multiplicity of a factor is the number of times that factor repeats itself. So for example, if you have x minus 2 squared times x minus 1, well, x minus 2 squared is actually on there twice. It's actually x minus 2 times x minus 2. So the multiplicity of that factor is 2. That means the multiplicity of the root of 2 is 2. Now, what the multiplicity does, that actually has an effect on what your graph looks like. If the multiplicity is odd, then the graph will cross the x-axis at that point. Now, the bigger the number, the more it flattens, though, as it crosses. So it says, think about y equals x cubed. So y equals x just crosses like this, but y equals x cubed bends as it goes through. So all of our odd numbers that are greater than or equal to 3, instead of just saying it crosses, we're going to be a little bit more specific. We're going to call it a wiggle, because your graph doesn't just go straight through that point, it curves as we go through that point. If the multiplicity is any even number, then your graph will be tangent or bounce at that point. So to show you guys what that looks like, we're just going to look at a little Desmos thing. All right, so the graph in red is x raised to the something power. So if x is raised to the first power, my 0 is 0. That's where it's crossing the x-axis. And then I also have, it crosses through because the exponent is 1. Well, if I move that to 3, it still crosses, but if you notice, it bends and gets a little bit flatter as it gets closer. Well, if I move that to 5, it still does the same thing, but it gets flatter, and that's going to continue as that value gets larger. So if you want to watch that run, as that exponent increases, it still crosses, but it's getting flatter and flatter and flatter through that point. All right, so now let's look at if it's an even number. Okay, so if it's an even number, so I have x to the second power. Well, x squared is quadratic. At 0, it touches, it bounces. If I go to 4, it still touches or bounces. It's just a little bit flatter. Same thing with 6, 8, 10, etc. So all of those even multiplicities will make that factor just be tangent at that point. It just gets flatter depending on how big that value is. So now it doesn't matter at 0, it matters at whatever that 0 is for that function. So let's go back to the first one, and instead of x, let's make that x minus 2. Well, it's going to be very similar, except it's going to happen at 2. So at 2, it crosses, it wiggles, and it's bending through that intercept. If I change the second one to make that x plus 3, well, now at negative 3, my graph is going to be tangent at that point. So what's going to happen with these polynomials is we're going to combine some of these together. So now if I combine this together and I make this, let's say, x minus 2 to the a, now this is how I get a polynomial. Because now my graph is tangent when it's even, my graph is crossing at that point because that one's odd. I make that 3, still crossing, but it bends. Same thing, it's still crossing, or still tangent at the b value, so it's still tangent here. And if I change that value, it changes just where that's happening. But as long as it's an even number, it's going to touch at that point. The odd number, it's going to cross at that point. The higher the number, the flatter the graph is. So let's go ahead and look at an example. So we are going to start just by finding the x-intercepts and determining what your graph does at those points. Well, since it's factored, it's easy to see if the x-intercepts. The x-intercepts are 0, -4, and 3. The multiplicity of those factors is the exponent of them. Well, x is raised to the first power. So at 0, the multiplicity is 1. X plus 4 is raised to the first power. So the multiplicity there is 1. X minus 3 is squared, so the multiplicity there is 2. Then we just determine what that means. Well, if the multiplicity is 1, then your graph will cross when x equals 0. Your graph will cross when x equals -4, and because this one's an even number, your graph is going to touch or be tangent or bounce at that point. All right, looking at b, very similar. We'll start with the x-intercepts, which are 0, 7, and -6. Then we'll determine the multiplicity. 0 is raised to the 5th power. 7 is raised to the 2nd power. This one is raised to the 1st. So what that means for my graph, at 0, your graph is going to wiggle. At 7, your graph is going to touch or bounce. And at -6, your graph is going to cross. Again, this is determined from the multiplicities. The x-intercept is where that's happening. So let's go ahead and take that and actually sketch the graph. Well, in order to sketch the graph, the only other information we need is the end behavior and the y-intercept. So end behavior, this function up here at the top, for example A, that was an even degree because it was 4, if I add up those multiplicities. And then this is a positive leading coefficient. So that means I'm going to be up and up. My x-intercepts are 0, -4, and 3. So I'll go ahead and plot those x-intercepts. It's also helpful to add the y-intercept, but in this case, we already have the y-intercept because it's 0, 0. Then I just need to see what does my graph do at those points. Well, at -4, my graph will cross. So I'm going to cross through that point. At 0, my graph will cross. So I'm going to cross through that point. At 2, my graph is going to touch. So I just bend back and touch at that point. And remember, those polynomials are just the smooth curves. They're not going to come to any sharp points. And that is what your polynomial looks like. What's nice about these graphs is that your end behavior is always going to match up with what you're doing at the zeros. So if you end here and your arrow was drawn here, that means we made a mistake somewhere in the process because it's always going to work out right. All right, let's try B again. So we'll go ahead and find our end behavior. Negative leading coefficient. The degree would be 8, so my degree is even. That means my ends are going to be down here and down here. So my zeros are 0, 7, and -6. And then again, let's see what we do at those points. So at -6, I'm going to cross through my graph. At 0, my graph is going to wiggle. So I'm going to turn and just bend as I go through the point. It just looks different than just straight crossing through. Again, it's kind of the difference between y equals x and y equals x cubed. Then at the value of 7, when x is 7, I'm going to touch that point. So touch that point, go back, and end where my arrow was. So on these graphs, you do not need to worry about how high or low or where those bends happen. As long as your end behavior is correct, your x-intercepts are correct, and what your graph is doing at the x-intercepts, that's going to be accurate enough. You're not going to be able to determine those points until you know calculus or unless you have a calculator. So the importance here is, again, basically the stuff's in this graph, or in that little box. The end behavior, the y-intercept, the x-intercepts, and then what your graph is doing at the x-intercepts. All right, this is just extra practice if you want to go ahead and try this one, or pause the video and try it, but that's what we did in the Pear Deck. All right, then moving on, very similar. The only difference here is that we need to factor before we actually sketch this graph. So factoring comes back again throughout this unit. In order to factor this one, let's take out our GCF. That means that my x-intercepts will be 0 and 2. At 0, my graph is going to touch. At 2, my graph is going to cross. End behavior, this is a positive leading coefficient, odd degree. So ends should look like this. And then we just mark our zeros. So 0 and 2. I touch at 0. I cross at 2. All right, on B, GCF first. So then my zeros here are 0, -2, and 2. At 0, actually at all of these, my graph is just going to cross. This was an odd degree. It was a third degree polynomial, positive leading coefficient. And then I just cross through each of those points. All right, on C, take out your GCF. I'm going to go ahead and take out the negative, just makes it a little bit easier to factor. Means my zeros are 0 and 2. At 0, it's going to wiggle because the exponent is 3. So any odd number greater than 1, it's going to wiggle. At 2, it's going to cross. This was an even degree and a negative leading coefficient. So my ends will be down and down. So my zeros are at 0 and 2. So at 0, I will wiggle and then cross at 2. Factoring on D, take out your GCF. To factor this, you can either do guess and check, or you can split up the middle. I'm going to go ahead and do just guess and check to get it done a little bit faster. So factors of 2 I already put in. Factors of 9, I can either do 9 and 1 or 3 and 3. I'll do 3 and 3. I need my middles to add up to a -3, which means this needs to be minus, and this needs to be plus. So that gives me those values. Then we'll just find our zeros. Mark our x-intercepts. All of those will be crossing because they all have a multiplicity of 1. So we'll go ahead and mark 0, -1.5, and 3. This was a positive odd function. And there's my graph. All right, on E, this one's actually a little bit trickier. So let's start by factoring. If I take out that -2, we'll notice that I have a sum of cubes. So square the first, change the sign, multiply, square the last. This trinomial that results from doing my sum of cubes is not going to give me any real answers, which means it's not going to give me any x-intercepts, which means the only x-intercept on this graph is -2. So this is negative and odd. End behavior, the x-intercept is -2. It's going to cross through that point. What we also know about this graph, though, is very easy, is the y-intercept. The y-intercept is -16, because if I plug in 0, that would be my y-intercept. So if I want to go ahead and mark that, I can. And I'm going to move that arrow so I have some space. And that is my function. Now you'll notice I kind of bended at that y-intercept. Now the reason I did that is because what I realized when I look at this function, that is a transformation of the cubic parent function. So that is the cubic parent function that's been shifted down 16, vertically stretched, and reflected over the x-axis. So what that actually means is that 0, negative 16 is not just the y-intercept in this graph, it's the point of inflection. All right, and then on f here, again, this is another one that's a little bit trickier to factor. This factors into x squared minus 9 and x squared minus 4. Both of those are difference of squares. So you get 4 different zeros. So this is going to have 4 x-intercepts, all of which will be crossing. This was an even graph. So I'm going to cross, 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 and cross. Now the last point that I probably should have marked before I drew it is my y-intercept. My y-intercept in this case is 36. The y-intercept also is really helpful to make sure our end behavior and our zeros are doing the right things, because all of these things together will combine. So we're going to skip G and H just because we've already done some very similar examples to those, but those are worked out on the notes on Schoology if you want to check those out. All right, so the last thing that we're going to look at is just writing an equation just based off of some given characteristics. So this tells us that a function is increasing on certain intervals, decreasing on a certain interval. It says f of x is greater than or equal to 0, which means it's positive on that interval, and it's negative on another interval. We're going to use that information to sketch a graph. Now, instead of just trying to freehand this and kind of make it work, let's look at what we know. From negative infinity to negative 2, your graph is negative. Then it switches at negative 2. Well, in order for your graph to change from positive to negative, I have to cross the x-axis, which means there has to be an x-intercept at negative 2. Your graph changes again at 3, so there's an intercept at 3. Your graph changes again at 5, so there is also an x-intercept at 5. So now I know the x-intercepts of this graph. The other information that it gives me, it says it changes from increasing to decreasing at 0 and 4. Well, if your graph changes from increasing to decreasing or decreasing to increasing, that creates a relative min or maximum. So now I know where this graph will have a relative min or max. So this graph will have a relative min or max, either one, when x equals 0 and when x equals 4. Now, where we put those in terms of height, there's a little bit of different places that we could do. So let's go ahead first. I'm just going to shade where this graph is positive and negative based on the information that I have. So it said that this graph was positive between negative 2 and 3 and between 5 and infinity. It said this graph was negative between negative infinity and negative 2 and between 3 and 5. So this graph starts off increasing until 0. So it's going to increase until 0 and then stop. So that means that there's a relative min or max at that point. Now, again, the y value of that could be anything. I could put it up here. I could put it down here. It doesn't matter what the y value is as long as it falls in the positive region. So let's just put it right here. So it's going to increase until that point. Then it starts decreasing. It continues to decrease until the x value of 4. Well, 4 is down here in the negative region. So I'm going to pick some y value in that negative region, and that's where my graph is going to change back to increasing. And that is my polynomial. Again, there's multiple ways that you could do this, but the x-intercepts should be the same, and then the y values of those 2 points could be different. It just has to be within either the positive or negative parts that's listed. Then from this graph, it says to describe the degree and the leading coefficient. Well, we know the degree, since my ends are opposite, I know the degree is odd. I also know it's at least 3 because there's 2 terms. So this could not be a first degree polynomial. If I saw 4 terms, I know it'd have to be at least 5. But again, the degree has to be 1 more than the number of terms at least. What I also know is that the leading coefficient is positive because the end behavior matches that. All right, so that is it for polynomial graphs. We're going to do just a little bit more algebra with our polynomial function than the next couple of days.